Hi everyone, I would like to ask all of you to raise your hand if you have seen this photo. I bet most or even all of you know that this is the first image of a black hole ever captured. This black hole is supermassive and as heavy as 6.5 billion suns. It locates at the center of the galaxy Messier 87, which is about 55 million light years away. Its image was the fruitful result of the collaboration of 8 massive radio telescopes which act as one Earth-sized telescope called the Event Horizon Telescope. This was a very exciting news to an astronomy buff like me, especially when it coincided with my independent study in the astrophysics of black holes. My name is Tintin, and today I will be your tour guide on an extraordinary outer space expedition. So hop on the spaceship, fasten your seatbelt, and enjoy. Let's start with the blue star. There are two basic types of stars, red and blue, just to give you some background information. Blue stars are heavier, hotter, brighter, and have shorter lifespan than red stars, so I like to call them rock stars. Stars generate energy by nuclear fusion. This causes an outward pressure to counterbalance the inward gravity. The heat energy also expands the star. Over time, the blue star expands into a blue supergiant. When it finally exhausts its nuclear fuel, it can no longer produce the energy it needs to counterbalance its gravity and collapses as a supernova explosion. If the star is heavy and large enough, it will collapse into a black hole. And this is how a stellar mass black hole is formed. Stellar mass is just one of the three size types of black holes, with the other two being intermediate mass and supermassive. Astronomers are still unclear about how intermediate mass and supermassive black holes are formed. It is easier to detect a black hole in a binary system, where the original star that forms the black hole revolves with an accompanying star, which later becomes a delicious meal for the hungry black hole to consume and gain mass. Besides, black holes gain mass from the infalling matter. Black holes can also lose mass due to Hawking radiation. When one of the particles in a virtual particle pair pop in beyond the event horizon, it spirals into the black hole, while the other one can steal energy from the black hole and exit as Hawking radiation. We will revisit the event horizon later. Now, we are going to approach our black hole. We first observe the corona, a cloud of highly energized particles. Scientists are still unclear about the location of the corona in relation to the black hole, but a theory suggests that the corona exists about the rotational pole of the black hole. Then we travel next to the black hole's jet. This cone-like structure is an outflow of ionized materials that emit radiations due to the interactions between the electrons and the jet's magnetic field. We gradually enter the Ergosphere, an invisible boundary where gravity from the black hole starts to become significant. We are spiraled into the accretion disk, which is made up of many layers of infalling materials that have come close but not quite yet fallen into the black hole. Somewhere among the accretion disk, there is a photon sphere, where incoming photons can stably orbit around the black hole for a period of time. The photon sphere, not the accretion disk, is observed on the black hole image we captured as the ring of fire. We then reach the innermost stable circular orbit, the innermost layer of the accretion disk. As we get nearer to the black hole and travel closer to the speed of light, we experience slower time and see objects around us shrinking due to Einstein's special relativity. At this point, we are supposed to be already fatally stretched or spaghettified due to the immense tidal forces of the black hole, but congratulations, we still survive here. Now we have passed the event horizon, the notorious point of no return. Nothing, even light, can escape from here. We have no choice but to be pulled towards the singularity. You may have known that the singularity is a point where an infinitely large mass is swashed in an infinitely small space, where density and gravity is infinitely large and space-time curves infinitely. Everything about black holes is infinitely crazy and strange, I know. A point singularity is true for a non-rotating black hole, But in reality, rotating black holes have a ring singularity. It is a theoretical possibility that the ring singularity provides a portal to the other side if the black hole is a wormhole. Let's say that's the case. We manage to survive the singularity and exit the wormhole to another point in spacetime. We travel back to our home sweet home planet Earth and our journey ends here. Looking back on my learning journey, I decided to embark on this independent study at first simply because I was really curious about black holes. I've always been fascinated with the mysteries of the universe since I was a child. I wished to develop my interest into something more serious and challenging, but still fun and engaging at the same time, so studying black holes came to my mind. Throughout the spring semester, I have had a better understanding in black holes through the lens of contemporary science, especially quantum physics, through an online course offered by the University of Alberta on Coursera. I also studied the fictional black hole in the movie Interstellar through Kip Thorne's book The Science of Interstellar to explore how science fiction of black holes is not fiction at all. In the end, I'm confident that this is my first step of my lifelong endeavor to unlock the mysteries of astrophysics, which will be followed up by the astronomy electives next year and possibly an astronomy related capstone project in the STEM certificate program at Pomfret and an astrophysics major in college. Everything is a possibility in astrophysics. Always remember that. Thank you for listening. I hope you enjoyed my independent study showcase.